Before proceeding further, let me reiterate Redshift free tier. I have got this write-up from AWS documentation itself in AWS Redshift pricing. First one is for serverless. So if you have never used Amazon Redshift serverless before, you are eligible for a $300 credit with a 90-day expiration towards your compute and storage use. Meaning, if you are using Redshift serverless for the first time, you'll get $300 credit for 90 days. So if you started today, for the next 3 months, you can keep on running Redshift serverless and you'll get up to $300 credit. So up to $300 will not be charged. But for provision clusters, it's a little different. For provision clusters, you are eligible for a 2-month free trial of DC2 large node and will get 750 hours per month for free, enough to continuously run one DC2 large node with 160 GB of compressed SSD storage. So this is 750 hours per month. If we run 2 DC2 large node, we can run only 375 hours. If 3 DC2 large node, we can run only 250 hours per month for free till 2 months. Once 2 months are over, you will have to pay the on-demand rate. Now you have fair amount of idea about Redshift infrastructure, how Redshift is hosted on node types. We use leader node and compute nodes. And while creating the cluster, we mention the compute nodes. Let's dive a little bit deeper into the architecture itself. Again, this is the diagram that I have captured from AWS documentation. So there are so many things here. It's a pretty busy diagram. On the bottom, we have storage. So if you are using RA3 node, we have Redshift managed storage, which is a combination of local SSD store in RA3 nodes and S3. We can query data which is there on Amazon S3 in Parquet, ORC or JSON format, a CSV format also. We do that using something called Redshift Spectrum. Then we have Redshift Serverless. And there's something called Redshift Data Sharing Clusters, which we'll talk about later on. But this is the one that we'll discuss now. Leader node and compute node, which you have already talked a little bit about. So compute nodes are the nodes which has local storage associated with it, and they are connected using AWS Nitro Systems network, high bandwidth network. And we can connect to Redshift either provisioned or serverless using JDBC or ODBC, using Redshift Data API. We can query live data using tools and clients, and we can run Redshift ML using Amazon SageMaker. Let's go deeper into the architecture. So this is the architecture you already know. So we have leader node. I am showing you 4 compute nodes. All of them have CPU, RAM and local storage. Now you can consider this as RA3 or DC2. Does not matter. If it is RA3, then we'll have additional storage in S3. Those will be block storage managed by Redshift or Redshift managed storage. Now this storage is basically the local storage that we get in either RA3 or DC2. Now what happens is that I am showing you only 3 CPUs per node. But internally, these CPU, RAM and storage are actually divided in something called slices. Let's say one CPU, certain portion of RAM would be contained in one slice, and that slice would be responsible for data processing of subset of data processing of the entire data. So this particular slice will not manage or process the entire data, only subset of data. So similarly, we can create multiple slices. So you can think of these slices as virtual servers inside of the compute node. And these are called node slices, which consists of certain percentage of CPU and memory of the compute node, and it is responsible for processing subset of the data, certain portion of the data which is there in that compute node for both DC2 and RA3. So that's what node slice is. It is nothing but kind of a virtual server with certain portions of nodes, CPU and memory. It also handles portion of the disk space or subset of the data, not the entire data. So if a compute node has, let's say, 128 GB of storage, and let's say it has 4 slices, one slice would handle or process only 32 GB of data. So this is the diagram that I had shown you earlier. Now it would make more sense now. So if you see the node types, RA3.XL plus single node, RA3.XL plus multi-node, 4x large and 16x large. So they have 4, 4, 12 and 48 vCPUs, 32 GB of RAM, 96 GB of RAM and 384 GB of RAM in 16x large. Now if you see the slices per node, so RA3XL Plus has 2 slices per node, meaning a single slice contains 2 vCPUs and 16 GB of RAM. In RA3.4x large, you have 4 slices per node, which means each slice contains 3 vCPUs and 24 GB of RAM. In 16x large, you have 16 slices and each slice contains 3 vCPUs and 24 GB of RAM. So now I think this slices per node would make more sense. Now you know what a slice is. It's a portion of node CPU and memory, and it handles subset of the entire data that the node contains. Now how much data a node can contain? So RA3.XL Plus can contain 4 terabytes per node. RA3.XL Plus multi-node can contain 32 terabytes per node. So a single slice can process 16 terabytes of data. Now in case of RA3.4x large, a single node contains 128 terabytes of storage or Redshift managed storage. So a single slice can handle 32 terabytes of data. Now in case of RA3.16x large, we have a managed storage limit of 128 terabytes per node, and a single slice would handle or process 8 terabytes of data. Now in case of DC2, it's a little different. So for DC2.large, we have 2 vCPUs and 15 GB of RAM, and it contains 2 slices per node. So one slice in DC2.large would contain 1 vCPU and 7.5 GB of RAM. In case of DC2.8x large, we have 16 slices per node. So each slice would contain 2 vCPUs and approximately 14 GB of RAM, or GB bytes of RAM. It's not GB, it's GB bytes. So I'll pronounce it as GB only. So this is what node slice is. Using RA3XL Plus, we can create up to a maximum of 16 nodes. Using RA3 4x large, you can create a maximum of 32 nodes per cluster. Using 16x large, you can create a maximum of 128 nodes per cluster. And in DC2, we can create 32 nodes per cluster for DC2.large and 128 nodes per cluster using DC2.8x large. Now, what is the purpose of node slice? So each slice would process subset of data. That means all of the slices can work parallelly. So in case of DC2.large, the 2 slices that we have, they will process data parallelly. In case of DC2.8x large, the 16 slices that we have per node, those 16 slices will work parallelly. So we'll get a parallelism of 16. So if we use, let's say, 4 nodes, then we'll get 64 slices. We'll get a parallelism of 64 because all the slices will work parallelly together. So that gives us an MPP system. MPP meaning massively parallel processing. So Redshift is an MPP system because we can create so many nodes in a cluster, and each node has its own slices. So 12 vCPU, certain amount of RAM, certain amount of storage. We can run complex queries in a much fast manner that can work on large amount of data. So if you use multiple compute nodes, all the compute nodes would do the processing in parallel using the slices that they have, and the result, the final result, would be sent to the leader node, and the leader node will do the final result aggregation before sending it to the client or the application. As you might have already guessed that Redshift distributes the rows of a table to the compute nodes, so the data can be processed in parallel within the compute nodes using the slices. The next architectural component is that Redshift is a columnar storage. Now, most of the data warehousing systems are columnar in nature. But what does it mean exactly? So let's say I have these records. We have order ID, customer ID, seller ID, order date, order amount, order status, and location. And I have 3 rows. In row-oriented storage, this is how the row would be stored. So this entire orange plate is a block. So the entire row is stored in one block. The next rows would also be stored in individual blocks. In case of row-oriented storage, the entire row is stored in one block. Now the question is where these row-oriented storages are used. In all the OLTP systems that you can think of, all the OLTP relational systems that you can think of. NoSQL also, because in OLTP systems or in operational data store, what we do is that we typically insert the entire row, update the entire row, or query the entire row, so on and so forth. So we do row-based processing a lot. So if you have, let's say, multiple columns in a row, we most of the times we access all the columns, most of the columns of that particular row, or for all the rows rather. So that's why it makes sense to store the entire row together in a block or in one or more blocks. So that's what row-oriented storage is. But in case of analytic systems, in case of data warehousing systems, we do not do row-based processing, meaning that we do not, most of the times, we do not query all the columns. Now, the number of columns are very less here that I'm showing. Typically, an analytic system or a data warehousing system would have huge number of columns, anywhere between 50 to 100 or maybe more. When we do query on that data on the analytic system or the data warehousing system, we do not select all the columns. So if we use row-oriented storage for data warehousing systems, and let's say I'm selecting just one column, so let's say customer ID, I have 3 rows. Now all the blocks have to be retrieved because I'm storing the entire row together in one block. And when I do IO, I have to do IO using blocks or at block level. So even though I'm getting only the customer ID and let's say the order date, only these 2 columns, I'll have to capture the entire block, or I'll have to fetch the entire block because that is the lowest granularity plot possible in row oriented storage. Now, as you can imagine that we are retrieving unnecessary data. We do not need the other columns. We are retrieving those. And as such, we are incurring more IO cost because even though we do not need most of the columns, we are getting the entire block. We are incurring IO charges for the columns which are not needed. So that's where column oriented storage comes into picture or was invented for this exact reason. Now we store the columns in blocks. So if you see, this green block contains only order ID values. So this is one block which contains only order ID. This block contains only customer ID. This block contains seller ID and so on and so forth. Now again, the block size is, I have shown it small, but that is not the case. But you can store a lot more values for a particular column. But each block contains values from only one column. So it does not contain values from other column. So now if I select, let's say, customer ID and order date, I will fetch only this block and this block. So I am not wasting IO at all. So I'm fetching data only which is necessary. A question might come, so if you are storing values of columns only, how do you know that which value is for which row? So how do we mix them? So there are pointers available in all the values. So it tells us that, okay, this value is for row number 1, this value is for row number 2, so on and so forth. When the database system shows us the results, then it shows us properly. So we do not have to worry about that. That is handled internally. But what I'm trying to say here is that essentially we are saving a lot of IO using column-oriented storage in case of data analytics and data warehousing systems. Because in data warehousing systems, we do not do select star. We only select certain columns. Now, one more thing is that, and another advantage of this is that as we store similar type of data in one block, the compression ratio can be very high. The data can be highly compressed. So we get 6 times, 10 times, even more compression ratio. So let's say you have 10 terabytes of data. If we store it in columnar storage or column oriented storage, it can become compressed down to 1 terabyte or 2 terabytes also. We have seen that in various scenarios that the compression ratio is very high, which in turn reduces the IO further. As we are storing 10 terabytes of data in, let's say, 1 or 2 terabytes, we are using lesser number of blocks using compression, and we are further reducing the IO. So IO is the most costly operation in relational database world because it goes and gets the data from disk. So more you reduce the IO, more performant the system becomes. So that's why I'm talking about IO so much. So the more IO we reduce, the more performance we get and less cost that we incur, because IO is very costly. So using column oriented storage or columnar storage, we store column values in individual blocks. One block would contain values from only one column, not from any other column. So using such architectural pattern, we can compress the data further, or basically database engines can compress the database further, which gives us lesser blocks and lesser IO and better performance. Now Redshift has something called zone maps, which helps in performance further. So let's see what zone maps are. Now this is the data. This is, again, I have created this data randomly. It has around 8 rows. What I'll do is, let's say each block contains 4 values of a column. So let's say these are the blocks. This particular block contains order ID column and only 4 values for simplicity sake. Same is the case with this block, which contains column customer ID, only 4 values. For this block, it contains seller ID column and 4 values, and so on and so forth. Now similarly, we have another set of blocks. So again, this block is for column order ID and it contains the last 4 values. This block is for column customer ID and contains the last 4 values. Now, what is zone map in Redshift? Redshift stores minimum and maximum values per block. Now, these blocks in Redshift are 1 MB or 1 megabytes in size. So in Redshift, one block is only 1 MB. And along with the blocks, Redshift also stores metadata of these blocks, which are called zone maps. So zone map for each block would typically contain the minimum and maximum value in that particular block. Meaning, this is, let's say, block 0. The minimum value in this block is 112 AR56 and the maximum value is 981 CYR3. Same is the case with this block, block number 2. The minimum value is 223098 and the maximum value is 981090. We'll have zone map for all the blocks. The size of zone map is very small compared to the block, in some bytes. Now what happens is, if we, let's say, select some value with where condition and we mention, let's say, where order date between November 2024 and let's say February 2025. Now what will happen, we are mentioning where clause in the order date. Now it can come and take a look at the zone map and see what is the minimum and maximum value. So should I read this block? So in this case, it will read this block. What about this block? Should I read this block? So here the minimum value is June 2024 and the maximum value is October 2024. So it is not going to read this particular block. Now you can imagine, I am showing you only a few blocks, and in a database which can store petabytes of data or terabytes of data, there are millions and billions of blocks. And if we mention where clause on a certain column, and if we can just take a look at the zone map, which is very less in size and the lookup is very fast, and if you can avoid millions of blocks and read only the blocks where the data is available, we are making the system perform much better. And that's what zone maps do in Redshift. So this is an innovation in Redshift wherein the block metadata is stored in zone maps so that we can skip some of the blocks to make the query run faster by skipping those blocks. I hope you have understood. If not, if you have any questions regarding this, please note them down and we can discuss the same in our live session.